Hi, welcome back to Math 533, Topics in Euclidean Geometry. In this video, we're going to talk a little bit about a notion of what's called a group. A group is a mathematical formalism that allows us to then talk later about symmetries of an object. So this is a really important idea, and this is very closely related to the ideas that Klein gave us for understanding geometry in terms of the symmetries of that geometry. So let's start with a review of some important bits of terminology that we have. So the first one is a transformation of the plane. A transformation of the plane, if you recall from last week, this is a bijection from the plane to itself. An isometry is a transformation of the plane that preserves distances. And because it preserves distances, all the other geometric objects that we're interested in are also preserved. Things like triangles get mapped to congruent triangles. That's by the side-side-side congruence theorem, as you saw in the homework. Angles get mapped to congruent angles. It preserves lines. So if I have 3 points on a line, the image of those 3 points are also on a line, and so forth. So an isometry preserves everything geometric. A reflection about a line was a transformation that you've thought a fair bit about, and the idea of this reflection is that we basically use the line as a mirror and look at the mirror image across that line. So one way of defining it is to say that P maps to P prime, where, so if P is on the line, it doesn't move, but if it's off the line, we want the line L to be the perpendicular bisector of the segment PP prime. Okay, and a really important technical tool we're going to use over and over again in this week's videos and also in future videos is the pointwise characterization of the perpendicular bisector. There was a reason that had a place of prominence in our first module, so here now in our second module it's going to be very important, and this says that a point P is incident to the perpendicular bisector if and only if PA is congruent to PB. Or in other words, if the distance between P and A is the same as the distance between P and B. Okay, this is our key review here. Now let's introduce the notion of a group of symmetries. So a group of symmetries is a special kind of set of symmetries. We say a set, here script G, of transformations of the plane. We call this set a group if it satisfies the following three properties. The first one is that the identity transformation is in my set G. The second condition is that if you give me two transformations that are in the set G, then the composition of the two, T composed with T prime, is also in my set script G. And finally, I want that if T is in script G, then T inverse is also in script G. So if you've taken an abstract algebra class, a modern algebra class, this notion that I'm describing here of a group is a special case of what's called a group, or an abstract group, if you want to emphasize the difference. Here I'm thinking of these as being this is basically a subgroup, for those of you who've thought about this, a subgroup of the transformation group of the plane, and you can think of the transformation group of the plane as basically the permutation group of the points of the plane. If you don't know anything about group theory, ignore that. Okay, so let's check that the set of isometries of the plane forms a group. To do this, so this is the set of all isometries. They're all examples of transformations, so this makes sense. And in order to show this, we need to check the three properties that we had on the previous slide. We need the identity transformation to be an isometry. We need that if T and T prime are isometries, then the composition T composed with T prime is also an isometry. And finally, we need to show that if T is an isometry, then T inverse is an isometry. Okay, so in this video, we're going to check the first and the third together, and I'm going to save the second one for you to do on the homework, and I'm going to step you through that process with a few directions of how to go about proving that. Okay, let's go ahead and check the first and third bullet points here. So the first one is kind of silly. Right? So the first bullet point is to check that the identity is an isometry. And so that's, let's let, I'll call it id, denote the identity. And now we just check, right? If, let's let A and B be 2 points in the plane. Then what we want to show is that the images are the same distance apart as A and B had to start out with, right? So this is straightforward to check. We look at id of A is A, id of B is B, and then tautologically, the segment AB is congruent to AB, right? So this was kind of silly. We didn't even need to write anything. This was a ridiculous thing to check, but I'm checking it just to make sure that we cross every T and dot every I. Okay, so 2 is on the homework. And then 3, so for number 3, what we want to show is that if T is an isometry, then the inverse of T is also an isometry. So let's let T be an isometry. So I have T is an isometry, which means that, so let A and B be points in the plane. Then if A prime is T of A, B prime is T of B, we have that A prime, B prime as a segment is congruent to AB as a segment. Right, so that's the definition for T to be an isometry. This is true for any pair of points A and B in the plane. So now what we do is we want to show that T inverse is an isometry. So for this, let's let x and y be points in the plane. And I'm thinking of these as arbitrary points in the plane. And now we want to show that x prime and y prime, the images of those under T inverse, are the same distance apart as x and y. Okay, how do we do this? Well, we're going to use the knowledge we have about x and y. By definition of T inverse, we now have that x is T of x prime and y is T of y prime. And now we apply the fact that T is an isometry to the pair of points x prime and y prime. And that's exactly what we wanted to show. Okay, I put the little QED box. It's not quite fully a proof because that second bullet point is one you're going to check on the homework. Okay, that's it for the notion of a group. In our next video, we will talk about how we can understand the structure of isometries of the plane in terms of reflections. Thank you for watching, happy mathing, and see you on the next one.